Hi, everyone. My name is Jackie Hernandez. I am the grad program manager here at UW Chemical Engineering. Thank you for joining us this evening for the Certificate in Battery Engineering info session. So we have a lot of great information, faculty lead here to help you better understand this new program that we're going to be launching in winter 2025. Oops. And before we get started, I'd like to do our land acknowledgement. The University of Washington acknowledges the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. We encourage you to check out your land acknowledgements wherever it is that you're tuning in. And just at a glance, you get to meet the team that's behind this program and who you would be working with if you join us next quarter. The application process, the program overview, as well as course overview. And the bulk of this session, we want it to be questions. So anything, comments that you have, we want you to answer those, not answer, sorry. We want you to ask those questions, and that's why we're here in this next hour. So I'm gonna let each and everyone introduce themselves. We're gonna start off with Professor Stu Alder, if you want to unmute yourself.
Hi, I'm Stu Adler. I'm a professor of chemical engineering, and I'm really excited to be starting this program.
And then we'll take it to Eric.
Hi, my name is Eric Stuvey. I'm also a professor in chemical engineering and also excited to see you all here today.
And I'll pass it on to Dave.
Sure. Good evening, everybody. I'm Dave Drischel. I'm the Student Services Director in the department.
And as I mentioned, I'm Jackie Hernandez. You've been getting a lot of emails from me. I'm the one that's going to be supporting you through the academic process, advising, and the application process as well. Speaking of the application process, the application is now open. So if you're interested after this or you're already excited about it, please fill out that application. The deadline is November 1st. That's the priority deadline. There is a little wiggle room after that, but we're really aiming for that November 1st deadline. And it's really simple. It's not as the application is not your typical admissions for like a PhD or MS program. You just create your profile, any contact information, your academic history, so the courses, degrees that you've had. And when you select the program, I made sure to write it exactly as it is on the application process. There's a few programs that start with engineering grad cert, so please be sure you select the battery engineering materials. And then here's a quick link that you can go directly to the grad school admissions page, and that's how you'll get started. And the program requirements. So, what we recommend is a bachelor's in chemistry, physics, chemical, mechanical, materials, or electrical engineering. If you have a degree outside of this with relevant coursework, please reach out and we can talk about if this is a right fit for you. But we encourage all of those that might meet these requirements to apply. And then this writing portion is also, again, not super long. It's just too simple, like it's a 1 and 2 questions. And then your resume and cover letter, and that's it. And there's no letter of recommendation required, nothing else, just these simple steps in these one page. A lot of you probably already have your resume and or CV ready to go. So you just upload those and you're all set. And then now I'm going to pass it over to Stu. He's going to give you a more detailed description of the program and courses and what to expect. So you can take it from here.
All right, thanks, Jackie. So I'm really happy to be here to tell you more about the battery certificate. We've been spending a lot of effort the last 6 months or so, in particular, kind of getting ready for the program. And I thought what I would do is actually just for everyone's time efficiency and give you a flavor of what it's like with remote education to give you an example. So a lot of times lectures will be pre-recorded. We don't meet in class and do lecturing. Instead, a lot of things will be pre-recorded, and then that leaves time during the Tuesday evening sessions to have discussions about either experiments that you've run or things that we're doing in the in-class exercises or on homework. So I'm just going to play this video, give you sort of a feel for the style of the course and the style of the pre-recorded media. And it also, at the same time, kills two birds with one stone because it answers maybe some of the questions you might have about the program. So let me just share this. Let's go to the next slide. So yeah, part of the motivation here when we started thinking about this maybe 2 years ago was just the incredible growth of the battery industry. There's just so much demand for battery engineers. Like all of my students were getting, they were doing things in fuel cells and all kinds of other related topics. And where were they getting jobs? It was all in the battery industry. And it's almost a perfect exponential growth as things have gone from small devices to large. It's just batteries are proliferating in everything we do. They've started becoming a major component of automobiles, and yet if you think about the battery industry as a whole, like who owns that? Like what engineering discipline owns batteries? And there isn't one. You can't say that chemies are the experts in batteries or that material scientists are the experts in batteries. I'm sure you're going to find people who are going to argue those things. But the truth is, it is a very highly multidisciplinary thing where there's a little bit of mechanical, a little bit of chemical, a little bit of electrical. It's all these, it's at a very much at an intersection between all these different areas of engineering. And so what that means is there's a dearth of engineers who know enough about all of these different things to be able to be super effective. And so I mean, just talking to people when we were planning this whole program, we just found a lot of people who are either in some other area of chemical engineering who wanted to move into the battery space, or people who were in the battery arena already, and they're like, "Oh, I want to augment my education in various aspects that I didn't learn as an undergraduate." Okay, so let's see. Let's move to the next slide. So that's where the Continuum College comes in. So the Continuum College, for perspective, this is a relatively new component of the University of Washington. And it basically the idea is to serve students after a post-baccalaureate degree primarily, and not people who are not going to just leave their jobs and come and do, like a 2-year research master's or even a 1-year coursework master's requires you to take off, from your career to go do this. This allows people to pursue further education at more at their own pace and be able to stay in their jobs and work, and yet still be able to take classes. And so that's why the focus on things that are like Tuesday or Thursday evening sessions, or some weekend courses. So it's part-time, mostly remote. So most of the students in these programs tend to be tuning in from somewhere else. A lot of it's asynchronous, although usually there's an asynchronous component that's online. And typical costs are somewhere between $15,000 and $20,000 to the student to get this 15 credit certificate. I will also mention that there's a really big push right now within the Continuum College and the College of Engineering to make these certificates stackable. So you're earning real, transcript recognized credits, and they all count toward a master's degree. And so the idea will be like you could take, a certificate in battery engineering, maybe you take another certificate from the Foster School of Business. Those two things stacked together would then constitute an official master's degree from the University of Washington in an engineering business combination. So different combinations of engineering or engineering and other sciences or economics. And that's another route toward a master's degree. Okay, let's go to the next slide. So yeah, I mentioned in the video this idea of the NatBat consortium. There's been a lot of work amongst the battery industry people, basically trying to identify gaps in people's knowledge. And this is not just for engineers, but across the whole scale for the entire workforce development, like from high school all the way to postdoc, like people who are doing research. And But what's interesting about those studies is a lot of it seems to focus, or a lot of the biggest gaps that people have identified, these are industry representatives who are talking, that a lot of it's at the bachelor's level. You have bachelor engineer who know a lot about their discipline of chemical or materials or whatever, but a lot of times that leaves big gaps in their understanding that's really important for batteries. And so that's what we've tried to focus the components of the program on. So the four main courses are designed specifically, basically, to address some of those needs. Things like understanding battery chemistry, understanding electrochemical measurements and interpretation of electrochemical data. These are things that are all kind of core to the program. Okay, next slide. So yeah, the other aspect of this that we've really struggled with early on was, well, how do you make a remote program that is also hands-on? And I think we're kind of getting lucky with batteries, because batteries can be small. So here's a lithium ion rechargeable battery, which has basically the same chemistry and physical processes and degradation processes that you have in full-scale batteries. So it is possible to study things on a pretty small scale. And here's an example. This is a PC board, which we had built specifically for the program. Basically, it's an interface board. You can take a battery of different types. We'll be looking at like hearing aid batteries, silver oxide batteries, all kinds of different types of battery chemistries that have different pluses and minuses. That's a double entendre. Did you get that? Did you hear that? And you can plug it into these boards, and that allows you to do a full-blown electrochemical experiment on them. And this isn't just necessarily, voltages and currents, which are relatively easy to control, but you can actually do some fairly sophisticated electrochemical measurements of the type that you would do in a real research setting. And there's a number of companies, but the one we've been working with is in the Netherlands. They make a potentiostat. It's not very powerful. Like, you can't do a car battery with this, but you can do a small battery that has the same chemistry as a full-scale battery. And it's called, the name of the company is PalmSense, because you can fit these electrochemical devices in your palm. So what you'll receive as a student in the course is you'll get a kit with one of these guys in it, and an interface board and some batteries and some other things that you're going to need to do the experiments. And that's part of the assignment. So you'll get these things at home. Most of these assignments will be laid out in advance with pretty good video tutorials on how to set everything up. Then you do your experiments. And then when you come to class, you're not just coming in cold or after a reading assignment. You've actually done something. You've done a measurement. Usually most of the measurements that I'll be assigning in the first course will have some kind of focus, like looking at different either thermodynamics or kinetics or transport phenomena, things that are related to the battery performance. And then that breaks the ice, and it also, I think, drives the discussion, like what are the important factors that we're thinking about. And then when we're doing the analysis or doing the homework problems, they actually tie into something that you've done, that you've seen in your own home, in your own hands. And I think that's in my opinion, that's a really valuable approach to learning something new for the first time. You also learn some practical skills, like how do you make a measurement and how do you interpret the data, things that are really important to the folks we spoke to who are employers who wanted to see this kind of thing in our program. Okay, let's see. Oh yeah, so I basically just talked about this slide. So the rest of the whole curriculum will look like this. Basically, it's designed to be done in a year, one major course per quarter if you do it at full pace. Battery Engineering 511 is sort of more focused on the fundamental ends of electrochemistry, understanding thermodynamics and kinetics and transport phenomena as it applies specifically to batteries. So it's a little bit like an intro electrochem course, but it's an intro electrochem course where where the vast majority of examples and all of the relevant stuff that we're talking about is very battery oriented. And then that moves on to battery engineering 512. That's what Eric Stuvey is teaching. He's either above me or below you, or below me in the stack of people here. And he's taking that and sort of moving more into the engineering of batteries, engineering of battery components, engineering of battery stacks, like when you put a pack together, the considerations for parallel and series cells, and things that you're measuring, and also things that you see that are related to degradation processes. Then finally, once you've taken those first two courses, the idea is you have enough kind of like of the basics of how batteries work and how they're engineered and what some of the issues are to understand what's going on at more advanced levels. And so Battery Engineering 513 is a bit more of a survey course that won't have an experimental component. We will be having between 2 and 4 guest lectures, depending on how much each of them does, who will come in and talk on various topics related to battery engineering. And I'll come back to what some of the subjects are. But that's the idea, is we're moving into an area that's more cutting edge, people who are working basically at the cutting edge of their field and looking at things like new battery chemistries, or thinking about what are the degradation processes in batteries and how to mitigate them, how to control battery systems. So things that are kind of the payoff of that more basic understanding. And then finally, Battery Engineering 514, that's the hands-on experience. And so that's what I described a little bit in the video. Everyone will be coming to Seattle. And so this is the one thing, the travel component that you need to think about. It's going to be hosted over a contiguous 2-week period, 10 total working days in Seattle. And that would be not this, that'll be in fall. So basically where the cycle here is winter, spring, summer, and then the last course is in fall. And that's when we're hosting this 2-week experience. So it's intensive. It's, you're there every day, all day for 10 working days. But it's very hands-on. You'll get to work with full-scale battery manufacturing equipment, battery testing. So your whole life will be batteries for a couple of weeks, but you get to spend it here in Seattle, which is always nice. And then finally, Battery 501, that is a seminar. We would like everyone to be kind of like exposed to what's going on in the battery world. There's a lot of activity on the UW campus on all the different departments related to batteries, seminars, people coming in who are experts, speaking on various topics. And it's just good. It's good to be exposed to that. So I think each of these will be like five seminars per quarter. There's a reflection that you have to write, but basically it's a way of learning the lingo, like what is going on in the battery world and how do people describe and talk about it from different engineering backgrounds. And that's pretty much the program. Okay, let's go to the next slide. So I think I described most of this in battery. I'm talking now specifically about Battery Engineering 511. So this is the first course in the sequence. Essentially, it's by a flipped structure. I won't be lecturing in the evenings. Basically, all of that will be pre-recorded, relatively short, punchy videos that kind of break it down to the basics. And then what we're focusing on mostly on Tuesday, Thursday evenings is talking about the experiments and working on the homework sets. And what I will be asking you to do is form groups. So we will have not just us as a resource, but also each other. So even though you might be in different parts of the country, you could still always the idea is to communicate outside of class too. And it's not just during the class periods that you're interacting. Okay. And then maybe actually, I think at this point might be best for me to introduce Eric Stuvey. Eric Stuvey, maybe you could wave. And he will be teaching Battery Engineering 512. So I will turn it over to him to describe what he's planning to do with 512.
Thank you, Stu. What I'd like to do is change, just make a small change here. We've been talking for about a half hour now. Maybe it'd be a good time to take a few questions, and then I'll start talking about the course that I teach. So if anyone has any questions, do the Q&A thing or raise your hand, and we can
That's a great idea.
answer them.
Yeah, feel free to put it in the Q&A box or raise your hand, and then if you feel comfortable, then you can ask the question live. I see we have Jeff. Yeah, go for it.
Sorry, I'm used to Teams, not Zoom, so I'm trying to figure out where the Q&A box is, but I couldn't, so I'm just gonna talk. I love your idea about the battery engineer is this chimera of disciplines. So looking at these courses, is this, so electrical, chemical, mechanical, material science are the four main disciplines in battery engineering. Is this a chemistry heavy course background? Are we going to get into pack design, BMS balancing, that type of thing? Or is it mainly focused on the cell structure and design of those?
Well, in battery, so in the first course, a lot of it will be focused on the cell because basically everyone needs to come up to speed a little bit on the chemistry aspects.
Right.
It is fairly chemistry heavy in the sense that we will be talking about like Gibbs free energy and what causes a cell to have voltage, and how does, how do we think about reaction rates in a battery, and how does that relate to voltage and current? So every chemical engineer will have to learn enough about voltages and currents to be able to understand that. But likewise, is the opposite is true. If I have an electrical engineer in the course, they have to come up to speed enough in the chemistry aspects to be able to understand it. So
Right.
so it's a mixture, but it will tend to focus more fundamentally in bringing everybody up to speed. And then it's really Eric's course that sort of takes from there. And so when you're talking about like pack design, battery management issues, those kinds of things, hopefully they've learned enough from the first course in terms of understanding what, C rates, voltage limits of cells, what is happening to concentration gradients in cells when they're being driven hard or being recharged. They know enough about that they can understand like what happens now at the pack level. You have a cell that's not the same as the other ones in the pack, and what's going to happen in that sort of situation. So it's sort of like we're trying to build things in layers, starting from the more fundamental side and then building up to the things that are more of direct practical significance. So it's very practice oriented. It is very trying to be very engineering oriented.
So are you going to, in the chemistry side, you're going to focus on rechargeable only?
Pretty much. There are a few, like I think it's instructive to talk about some types of cells that are not rechargeable just to understand things like cell thermodynamics. But for the most part, we'll be focusing on rechargeable.
And will you be discussing the different flavors of lithium ion, like LCO, LTO, NMC, that type of thing as well?
Well, to some extent, yes. So students will be aware of that going into the third course, but the third course in particular, that's the one where we really start to break out into like looking at different types of battery chemistries.
Okay, so like why I would choose LTO over NMC, for instance, or LFP versus all these
Those types of specific things, yes, that
Okay.
it's going to be more in the third course.
Okay.
So yeah, I'll say a little bit about what we do in the second course, like Stu said. The second course is comes from a different direction. You say, okay, what is my application? What do I need? How does that drive my selection of a battery or the sizing of the battery? We fold in, okay, what are the fundamentals you need to know in making that selection? But we are always focusing more on the applied type side. So I mean, you mentioned packs, Jeff. One of the things I like to talk about is like Stu said, I call it weak cell theory. So suppose you have some pack, and it turns out that having one bad cell can really cause a lot of damage in the way that the pack functions. And we spend time looking at that. You can do it by saying, Well, suppose one cell has a higher resistance. What does that do? That you can actually solve for that analytically, but we can also model it. We can say, what happens if one cell has a lower charge capacity? For example, it's an older cell degrading faster, and you can propagate these effects on how the pack behaves, and that forms the basis of understanding battery management systems. I'm also going to talk about thermal management, which is quite important in lithium batteries. One of the things we do, because of the potentiostat has a voltage limit, it's hard to study batteries in series, or that is lithium batteries in series, because they're high voltage. 3.7 volts, you start stacking them up, you get high voltages. So instead we use nickel metal hydrides, and you can get 2 or 3 in series, they're only 1.2 volts, and then mimic all the pack performance that way. So, we try to work things around, do things as flexible as we can.
Thank you. Appreciate that. Thank you. So did you mention you're doing thermal, so you are covering mechanical attributes as well, with the thermal issues and thermal management?
Yes.
Okay, awesome.
Eric,
Any other
would you like
questions?
to continue?
Yeah, I'll continue. So basically what I've said is already in the slides, so we'll just continue. Why don't you show the slides, Yaki? And I just described the teaching philosophy. We start top, go identify the applications, requirements. That informs how we design the pack and how we optimize it. The hands-on will give you, we'll have remote labs and demonstrations, and we did this in our first run courses this year. And these will also let you look at representative cases for battery performance and design. And all of this is informed by the fundamental properties that you got in the first course, so that everything holds together, hopefully seamlessly on that. Next slide. And here are the learning objectives. There's a lot of words on that slide, but let's basically relating performance of real batteries, differentiating different battery chemistries. And for that, I mean, not the specific differences in lithium anodes and cathodes, but comparing lead acids and nickel metal hydrides and lithium batteries and so on. So you get to see where they place. Key aspects of battery performance, voltage, current, power, charge capacity, reversibility, and capacity fade. And all of these you can measure with that little potentiostat. That is a full-fledged scientific instrument. Designing battery packs, like I mentioned, and looking at the function of how battery and thermal management systems function. Next slide. Again, here's the topics are covered. You can see that a review, how to do battery measurements, stacks and packs, modeling cell behavior, thermal behavior, battery management systems, and battery system design. Next slide. We've done a number of student demonstrations, and so what we did here is that the students, I gave them a topic and said, do the demonstration and do this. They have essentially no experience in electrochemistry other than the first course, little experience in how to use the potentiostat, and they had a week to do this, and they came up with some great videos on this. And I'll show you some pictures from the videos, but the demonstrations we did are charge and discharge curves of primary and secondary batteries, constant current and constant voltage charging, which is the common way to do lithium cells, lithium ion cells, effective C rate on battery potential and capacity, voltage recovery and current interrupt, and the weak cell theory with series and parallel batteries. Next slide. So here's a scene from one of the student videos. This is the connection of the potentiostat to the battery, and the student there is giving a thumbs up. Everything's working, and you can see the little potentiostat there. And in the gray box in the background is the case that it comes in. It's a nice little carrying case. And there's a little AA or AAA nickel metal hydride being hooked up to the system there. Next slide. And here's some of the results that he has measurement of discharge curves for 2 different C rates. Again, this is on an Energizer nickel metal hydride AAA, And the comparison with the manufacturer's discharge curve, that's the inset, you can get these on the web, is not too bad. I mean, you have the red is the high C rate, and the blue or the blue line is the low C rate on the actual data, and there's a good comparison there. So it does work out. Next slide. Also, they did a study of pulse discharge tests, which is a common industrial way to measure battery resistance. And so you have the battery functioning, and then you put pulses on it. And so you can see that in the upper curve, there's a pulse up and pulse down, and you can measure the resistance from the sizes of those pulses. The green line is a healthy battery, and the black line is a weak battery. Its cell resistance is decaying with time. So, and we'll go on from there. Okay, cell resistance is increasing. The voltage is decaying with time. And so this is one of the things, you can have a weak battery that behaves, like a healthy battery at first glance, but then you don't realize, oh, the resistance is going down, and it could have happened because of some damage in it was overdriven, overcharged, or not operated at the proper C rates, and it can otherwise look healthy, but is not. And so we have ways of testing that. Next slide. Here's another student demonstration. So here they studied discharge, in this case, of a D cell, a nickel metal hydride D cell, and you see these two white blocks behind it. And those are, each block is a 0.2 ohm resistor. It's actually 5 1 ohm resistors in parallel. And so the two blocks in parallel is 0.1 ohm resistors. That's a really high load for this. And the voltage being measured in this particular case is 0.6 volts rather than the normal 1.2 it's rated on. So it's really got the battery loaded down. But the nice part about high C rate discharge is it doesn't take that long. So next slide. And here's some demonstrations then of the discharge curves for DC and AAA cells under the two loads. The 0.2 ohm load is up on top, and the red line is the C cell, the blue line is the D cell, and the green line is the AAA. And so you would think the C's and the D's on the Energizer batteries are really close. They have practically the same specs, okay, which is kind of unusual. The AAA is, of course, a much smaller battery, but the C and D cells are not lining up in this curve, and that's because one of the batteries is damaged. And this was a student video, the student demonstration. They got through it in a week. It's kind of a bit rushed on that, and so they didn't realize that one of the batteries had been damaged because of the way that they had done the charging and discharging. But hey, that's all part of the process of learning this stuff. Next slide. Now students do projects and group work. And here's one I particularly like. The students pick their own projects, and this group picked batteries for CubeSats, these little satellites that are launched into space for a variety of purposes. And the challenges were to look at capacity loss, polarization loss, and thermal runaway. And because the conditions of space are quite extreme, radiation, vacuum, thermal fluctuations, and vibrations on takeoff. So I'll go to the next slide. And I really like their report, so I reproduced 4 slides from their reports. The drawings are really nice. They look at the extreme temperature fluctuations as the satellite is in low Earth orbit. It's going from really hot to really cold every 90 minutes. That's a lot of stress. Vibrations on takeoff can really damage the cell. Vacuum effects you can have outgassing, and that can lead to boom, as the little red star shows you, and overall battery effects. That is the cycling of the batteries, the constant changing in sunlight and dark really places a heavy load on the batteries. Next slide. So I put some student comments in here, and I'm not going to go into all of this because they're really nice and they were positive. And so basically students like the class. And I'll go to the next slide, which is what aspects contributed most to your learning. And the students, they cited the homework solutions. homework is really important, and that's where you learn things. They liked the demonstrations, and they liked, the overall way that the class was run. So I think that's my last slide. And so open it
Yeah,
up.
so I'll just mention that Eric and I have both run pilot versions of these courses on campus as sort of a way of as a foundry to basically develop the material. And that was a common theme. Basically, students loved in-class either in-class experimental demonstrations or doing their own experiments. That was that was a positive experience for many students, being able to do things hands-on.
Awesome. Well, thank you, Eric and Stu, for giving us a detailed run through of the program and courses being offered. So now we still have some time. If you have any questions, you can use the Q&A feature. You can go to more, the little circle with the 3 dots, and it should be there. And you can type in your questions, or if you feel comfortable, you can raise your hand and you can ask your question live. But this is the time, this is a program, if you are interested, you have the lead faculty here to know the content of this program for the next few quarters if you were to join. So really great time to ask those questions that you might have. Stop sharing.
Yeah, question. Are you guys going to be covering some of the more advanced techniques like EIS when it comes to impedance measurement, or looking at newer technologies like silicon anode, solid state, some of the things that are over the horizon? I believe your seminars are going to address that. Is that correct?
The seminars will address that to some extent. There'll also be a module on, current topics in battery materials. That'll be part of the 3rd course. That won't be a hands-on thing, but the students will learn and be aware of those things.
Okay.
Yeah.
The potentiostats can do their own EIS.
They
So
can.
this
The
is really
student,
nice.
as part of the 1st course, they will do one EIS experiment.
Oh, awesome. Okay.
Yeah.
I didn't do EIS in the 2nd course, but I will the next time I teach it.
Okay. Yeah, it's the new thing for batteries. So, just as a comment, I look at this course and I think it's really fascinating, interesting to have something like this available that addresses the uniqueness of batteries, that they are not a single discipline thing. And I love the fact that you guys are addressing that way, where I bring in electrical engineers and it takes them years to become battery engineers. Same thing with my chemical and my material scientists. So I really do appreciate this being available now as a learning option for our team. So thank you so much for.
Yeah, sure.
Yeah.
Yeah, thanks for that comment, Jeff. That reminds me the student in my class, the picture, he was the thumb of the thumbs up in the picture of the student demonstration. His mother is a power engineer. So he is a chemical engineer. His mother is a power engineer, and he would go home and tell his mother what he was doing. And oh, sure, she said, oh, she really got into this and got into all the power aspects of batteries. And
Right.
the things is, Stu and I, we've taught a lot together for, gosh, more than 20 years. We've actually done a fuel cell course. We've done it online already many years ago. But one of the things we learn in fuel cells, especially for chemical engineers, is that chemical engineers don't know a lot of electrical engineering, and they need to know this stuff. And so, when you start doing impedance, the idea of impedance matching for optimum power transfer, that's important in batteries, and that's definitely an electrical engineering concept, but it's important for us to work into how we describe the batteries.
Yes, that's one thing that we actually created a special job description at Microsoft as a battery engineer, and it is this ideal of the multidiscipline engineer that can having electrical engineers, understand redox equations it's fun to observe, and it's also good. I'm a double E myself, and it's also fun for my PhD material scientist to look at a schematic of a BMS and what is this? I have no idea what this is telling me. but the battery engineer needs to have that discipline or that language across those disciplines. So
Yeah,
really,
even if they
really,
don't, yeah, even if they don't know it, they know
Yeah.
where to go.
the
who to
doubly
talk
has
to.
to be able to converse, yes, has to be able to talk to that material scientist and
Mhm.
vice versa. And there is that common battery language. So I really do applaud you guys for this. I think this is going to be a great resource for us to take advantage of for our team and trying to build that ideal Chimera engineer. And that's so, yeah, thank you. Thank you.
Hey, can I take a poll of our guests?
Yeah,
How
go
many
for it.
people, how many, raise your Zoom hands if you're a chemical engineer? We got one. I can't see all the people on my screen, but two. Okay, how about electrical engineering? Got one,
Mhm.
two. Others, where are your other, just chime in, where are your other expertise? Where do they lay?
I just opened up the chat, so feel free to put it in the chat.
I was mechanical and then more recently a robotics engineer.
Cool. Good. We used to do our fuel cell program was along with the mechanical engineering department here. We would have like about 30 mechanical engineering students and about 10 to 15 chemical engineering students building fuel cells. So learned a lot about how MEs think. Others?
I have a background in chemistry, fuel cells and batteries.
Okay,
Mhm.
very good.
I just finished my bachelor's in MSE at UW, and I pretty much put all of my elective interest into clean energy and electrochemical materials. So I did a capstone project with Group 14 actually, and then my senior research project was in the test beds, so I'm actually really familiar with the lab already.
Perfect. Yeah,
Yeah,
that's
so
perfect.
How do you
Yeah.
how do you like the test beds?
oh, it's great. I mean, it's like you were saying, it's a really valuable resource. And actually, even since I've finished my degree, I've still been volunteering to continue some research on like the perovskite solar cells that I um, helped to make with my mentor there, and partly just to kind of I don't know. There's a handful of just really brilliant research scientists that you can pick the brains of at any point in there, and then getting trained up on AFM and SEM as well. So just kind of
Did you attend the event last Friday?
no, no,
No,
I
well, they talked about a new expansion in their test beds, which is coming next year, and the governor came and gave a talk, and this was all really a cool thing. This is quite a big deal. You had people from Group 14 and uh, Big Bend Community College, they go into this quite a bit in Moses Lake because that's where a lot of battery companies are. It was a very inspiring event that they had.
Yeah,
No.
Mike's plan is that will be online by the time the students are there.
Yeah, okay.
It was very cold.
Oh, you were there? It was cold, yeah, I remember.
I do have some direct questions. Maybe you can help answer Stu or Eric. One has to do about the at-home kits. How do the at-home experiments work? Will they need anything special? And along with that, do they buy them? Do they rent them? How
Good
does that work?
questions. Yeah. So everything's pretty small for at least for the first battery. Actually, for both courses, the kits are relatively small. I was showing you some of the hardware earlier, but basically it comes in a box. Here's what you get from Palm Sense. Looks like this. We add some stuff to it and also send you some batteries. But yeah, the volume of it is not big. And we're also going to send a bunch of other things home too, some safety stuff. There'll be like all the wiring you need, all these things. I think the only thing that we won't be able to provide is a PC. So if each student will have to provide their own PC, but that's usually most people have one. And if you don't have one, you can buy one relatively inexpensively. So that's the one cost that we're not covering basically. But as far as receiving the kit in terms of cost, you don't buy it. We're basically buying them in bulk from the company. It's in the Netherlands, and then we're adding our own stuff to the kit, and then we're sending it. So you have everything you need to do these experiments. You don't pay for that as a fee or anything. It's amortized in the credit hour fees. So you're already paying basically on a credit hour basis. And then we send you the kit and you keep it. So you have your own Potentiostat at home. We don't ask for it back. We're not lending it to you. You're keeping it, which I think is kind of a cool thing about the course.
I need to put in one little extra point about the PC thing, that the Potentiostat requires a PC. It doesn't work with a Mac. And but I'm a Mac person, but to use it, I mean, you can just get a $400 PC and it works fine. It's great.
I will also say I did extensive work trying to find a way of getting it to operate on a Mac, and I don't recommend that. So
You don't have
Much
to.
easier.
You don't have to. So that cost is that's a totally loaded cost then.
yes,
Awesome. Thank you.
you don't pay extra for that.
And I do have a couple more questions related to the class structure.
Mhm.
So how would a student access their video lectures or online resources? You
Mm.
mentioned there's going to be pre-recorded lectures. Where would they find all that information
Gotcha.
once
Yeah.
in the program?
So there's a bunch of different types of learning management systems, is what they're called, for universities. Universities usually have maintained contracts with a number of different companies that provide this kind of software. And UW uses Canvas. So that's all built into the cost structure of the certificate. Basically, you have access to Canvas and the Canvas page for the course. And we use Panopto, the Panopto recording feature. So basically that you can also upload videos to the Panopto database, and it's available to students who are registered for the course on Canvas. So it's really easy to gain access to the videos. That's also the main interface for passing back in materials. So written materials, things that we're asking the students to read, or submission of homeworks and feedback on homeworks and that kind of thing. That's all through the Canvas interface.
Great, thank you. And then another one related to courses, how are the homework and tests like a regular, typical college course, or is it going to be a little bit different since it is at a graduate level?
It's pretty typical for a graduate course. We basically tend to grade on an A through C scale in graduate courses. And in my case, in Battery Engineering 511, I typically have a very specific set of learning objectives, which I share with the students. That is usually expressed in terms of things the students either know, can explain, or do by the end of a period of learning. And I'm very strict about that's the content of exams and quizzes. So the way battery engineering, there will be exams as part of the course, but it'll be extremely tied to what the students are doing in class and in the exercises. So hopefully is fairly straightforward. We're not trying to, there's no gotcha games that we're trying to play with people. We're basically the assessment is very direct to the material. Basically, were you there? Did you participate? There's no reason that someone who's fully participating in the course wouldn't do extremely well.
Great. And then I do have a two-part question. What are the typical online evening classes like? And can you do well in the courses without attending those online sessions?
I think it would be very hard to do well without attending the online sessions. It's the main interaction. So, that's the downside of remote learning is this inherently built-in lack of interaction. You're by yourself, you're watching videos. So we as the instructors, we're doing everything we can possibly do to counterweigh that sort of built-in weakness of online learning. And that's what Tuesday and Thursdays focus on, like getting people talking about their measurements, talking about the homework, having really dynamic, interactive discussions that really dig into the material and put the finger on the point, like what is it that we're trying to learn, and what is the main thing to take away? Because it's sometimes easy to miss that if you're just by yourself.
Sounds good. I think those are all the questions that I'm seeing. Any other questions, please put them in the Q&A or raise your hand. We are at 7 o'clock, so I do want to be mindful. Megan.
Hey, thank you all for hosting the session. I had a quick question. I might have missed it. I was finishing up some work, but when was the 2-week in-person session at the test beds? When was that occurring?
That'll be in the fall. So the following fall.
Okay.
So the cycle of we're not following the normal academic year. So instead of starting in fall like you would with many programs, we're tilted one quarter. So we're starting in the winter, and it's going to go winter, spring, summer are the 3 main courses, and then fall again. That following fall is when the CEI experience is. We haven't scheduled it yet exactly within the fall, but it'll be one contiguous 2-week period in the fall quarter.
Okay, thank you so much. I appreciate it.
Yep.
Any other questions or comments? Well, with that, I'm going to wrap it up. Thank you all for joining us this evening. I will send out a copy of the recording and the slide deck for if you have any questions. The contact info, the emails that I sent out, please don't hesitate to reach out. Applications due November 1st, and we're all open for any questions. This concludes the session, but we're going to stick around a few extra minutes if you just want to hang out and just talk informally. Thank you for coming this evening.
Thank
Thank
you,
you.
everyone.